All right, so we've talked a little bit about charge, and we recognize the concept that current is charge over time. Charge over time. And I want you to recognize that that is measured in amps, and we're going to get familiar or more familiar with that as we go. But an amp is a coulomb per second. Now, secondly, you want to ask the question, why might current flow in the first place? Now, this is the goal of the activity that I had you try to work on. I apologize, the mail hasn't helped us out a lot. Hopefully the sim has started to get you thinking about it. But I know what you're able to see. It's probably not a big surprise to you, but if you take a light bulb and if you connect some wires, what you'll begin to discover is, of course, you could make that light bulb light. You'll discover that if you hook up some wires, eventually, oh yeah, the light bulb turns on. And in the process, I want you to think about why that is. What's happening? Well, you know that a battery is a source of energy. So we got to pull energy ideas into this. And that's really the key I want you to focus on for a few minutes. Batteries are sources of energy. And we can measure how much energy there is. And we're going to do it like this. We're going to use a concept. I'm going to give it the formal name. And the formal name for this is electric. Sorry about the scribble there. The formal name for what we're going to measure is called electric potential. Now, electric potential is a neat idea. Now, be careful. It sounds a lot like electric potential energy. It's not. It's similar, but don't let that confuse you. Electric potential is the term that we're going to use to refer to the energy in a battery. To be very specific, electric potential is defined in the following way. It's the amount of energy that is available per charge. Now, we just talked about the idea that from a battery, energy can light up a bulb. Well, the concept is, as you know, inside that battery are a lot of atoms. And of course, those atoms have as a part of them electrons and protons. And you recognize that those electrons, negatively charged particles, can flow through wires, because of course the wires have them too. And those electrons travel, notice the direction I'm showing is weird. They travel out the negative side of the battery and they travel back around. And in the process, of course, they go through the filament and we end up with light. But electrons travel because there is energy available to them. And again, we measure that energy per charge as a ratio called electric potential. So let's talk about units for just a minute. Not a surprise, energy is measured in joules as usual. So we're going to measure the amount of energy in joules. At least I'm going to try. I might just need a J there. There we go. And charge, once again, is still measured in coulombs, as it has been in the past. And I want you to recognize a new unit here. If we're talking about energy in joules per coulomb, that has a very familiar name to most people. And you'll recognize it as soon as I manage to write it. So joules per coulomb is the units, or are the units that we use for energy and charge, but together, I'm going to get it. Together, well, use your imagination over there, please. We refer to a joule per coulomb in a new unit, which is called a volt. Now, I know you've heard that word, V-O-L-T, volt. And a volt is the amount of energy in joules divided by the amount of charge in coulombs. So volts are energy per charge. The units, volts, are equivalent to the units, joules per coulomb. The term electric potential is really the official and most correct name to use, but maybe out of sheer laziness, most people, myself included, tend to refer to this term or this quantity as voltage. Now, that's kind of a weird word, voltage, but of course, voltage is the term that we use to measure something measured in volts. Bottom line, key idea. Hey, we are going to think about the energy available as voltage, and we're going to think about the result of energy being available as current. So if you look at this picture, hey, we have energy available from a battery. And as a result, it causes charge to flow, and we measure the amount of that charge flow as current. So those two things go together. Now, a couple things to pin down here. You'll notice that this battery shows negative particles going around this direction. That's what happens. However, that's not really what we use to have a conversation about it. We tend to talk about charge flow as positive charge moving. That's weird. I'm going to show you this PhET sim. It's pretty neat. I want you to play with it. Hopefully you have. Here's a PhET sim. Here's a light bulb. Here is a battery and a wire. And I think I'll toss a switch in there too. And this is kind of neat because it allows you to notice we can build a circuit. Now you'll notice the blue things in here represent electrons. And if I turn the circuit on by clicking the switch, you see the electrons are moving out of the negative side of the battery around through the filament and back. That's actually what's happening. Now, strangely, you'll notice up here it says show current, electrons or conventional. If we flip this over and show conventional current, the conversation most people have in physics land when they talk about current is that it flows from positive to negative. That's not really what's happening, yet it is the conventional conversation we have. And honestly, the reason is because Ben Franklin screwed up once, but that's another day's conversation. But know that what's really happening is electrons are moving from negative to positive, though the conversation we usually have is that current flows from positive to negative. All right, so two key ideas. Current, that's the flow of charge per time, and voltage, that's the amount of energy per charge. Those are big ideas that I want you to grab onto.